Hi. So, these set of videos are going to be looking at how data is represented in a computer. So, we're going to look at specifically text and images. So, we'll look at bitmap and raster images in another set of videos. But for this video in particular, we're going to look at how symbols are stored in letters and what have you. So, basically using the ASCII table in Unicode. So, without further ado, I'll get straight into it. So, as you're probably already aware, your computer literally just stores numbers of ones and zeros. So binary, that's something we've been talking about a lot recently. And the way that it will represent a letter on a computer is by having a numeric value stored with it. So as you can probably see on here, so we'll have a look at the letter A, this one. This number is 97 on on a computer. So the number 97 in binary. So 1, 2, 3, 4, 5, 6, 7. So this is obviously 8 bits. So using a byte. So this is a byte. So using a byte of data, we get the letter A. Now, obviously, when a computer just reads this, and if it does use 8 bits, so say you've got other numbers either side of this, then obviously it'll just read this as A and then B and then C or what have you. And this will make sense when I show you the hex editor in a second. So all you need to know is that for now, a PC will store a letter symbol or a number that's displayed on screen for the user as a set of binary digits like this. Now, that's A. So if we look at uppercase A, so actually, capital A, this is 65. Now, 65 in binary is this. 1, 2, 3, 4, 5. Yeah, there we go. And that equals capital A. Now, what's the difference between this one and this one? And the main difference is this 6-bit here. So underneath this, you can see that for a lowercase a, it's 1, and for an uppercase a, it's 0. Well, let's have a look at B. So what's the case for B? So B is 98, as you can see on here. So 98 is 11000010. So that's 98. And uppercase B is 66. So obviously just one up from this number here. So 0, 1, 0, 0, 0, 0, 1, 0. So that's uppercase B. Again, you can see that the difference here is this one. So the 6-bit. So if the sixth bit is 1, then it's lowercase. We'll make that LC. So lowercase. The 6-bit is 1. If this 6 bit is 0, it's uppercase. Whoa. Don't know what happened there. There you go. Uppercase. So that's an easy thing to remember, and the reason why a computer does it like that is because it's easy to switch between one and the other. So to switch between say a lowercase b to an uppercase b, you can use a mask. Now, a mask is just something a computer will use. So instead of having to literally be like, right, what's an uppercase B, and looking through, this entire list to try and find what an uppercase B is, you can literally just use the B that you've already got. So if you've got a lowercase b, so we've got 0, 1, 1, 0, 0, 0, 1, 0, you can times it by a mask. Now, this mask is going to look something like this. So 1, 1, 0, 1, 1, 1, 1, 1. Now, this mask, you can use an AND operation, which we've done before. So an AND operation is if two inputs, if they're both 1, then the result you'll get is a 1, but anything else is a 0. So as you can see, this would be 0. These are two 1s, so that'll be a 1. That's 1 and a 0, so that's a 0. 1 and 0, 1, 0, 1, 0, so 0, 0, 0. 1 and 1 gives you 1, and then a 1 and 0 gives you 0. And that gives you uppercase B, which is the same as this uppercase B here. So to swap between one uppercase and lowercase on the ASCII table, it can literally just do that. Now, one thing that I will show you as well, obviously with this ASCII table, you might be thinking, well, what's the point in having like these numbers associated with them? Like, why not just make it something that's easy to remember? Why is A not 1? Well, technically speaking, it is. So if you look at, say, 97, so 97 in binary, 0, 1, 1, 0, 0, 0, 0, so 1, 2, 3, 4, 1, 2, 3, 4, 5, yeah, so that's 8, so that gives you A. Now, if we ignore these first 3 bits here, so let's just get rid of them for now, you're just left with 0, 0, 0, 0, 1, which is technically the first letter of the alphabet. Let's have a look at B. So 1, 1, 0, 0, 0, 1, 0. Now, if we get rid of these 3 at the beginning, you're left with 0, 0, 0. Obviously, that would equal B. 0, 0, 0, 1, 0. That equals 2. So this is the second letter in the alphabet. So as you can see, it goes up sequentially. So we could look at anything. So if we look, say, at number 5, for example, so obviously 5 in the alphabet is, I mean, this is silly, but A, B, C, D, E. So we know that E is going to be the 5th letter in the alphabet, right? So if that's 5, we know that 5 in binary is 1, 0, 1, that's 5. Now, if we put these 3 bits back on here, so we get 1, 0, 1, 1, and then we put the remaining zeros in, which I think is just 2 zeros, to give you 8, which it does. What's this number? So this number here is, it's 64, 32, 4 and 1 obviously for 5. So this would be, should be 101, which if we look at 101 in the list, 101 is actually E up here. So that works out fine. So literally, it's easy to remember because you just remember that for an uppercase or lowercase letter, it's 0, 1, 1, and then whatever number it is in the alphabet. So obviously, if you want in say C, you just go 0, 0, 0, yeah, 0, 0, 0, yeah, 1, 1, which gives you C. And then if it's an uppercase C, you just take that one out and make it 0. That gives you uppercase C. So it's quite easy to do, and that's why they use it like that. So I've used a piece of software to have a look at this file in particular, and I'll show it on screen now. So this file in particular, I've literally made a text file, just call it whatever, test.txt, and I've put these things in. So hello world, and this is a cool fish. And I've put a new line in, so this is on a new line. So how would the computer actually interpret this? Well, I have put this in the hex editor on here, so you can see it, and it actually goes through each individual hex value on here. So as you can see, you've got 68. So 68 in hex is H. So let's check our ASCII chart on here. So 68 in hex. So you got to make sure that it's on the hex thing and not decimal. So 68 in hex, we can see, is actually a H. So that's correct. Same for 65. So 65 is E, which if you go 3 back from H, you do get E, obviously. So that checks out. 6C, 6C for L. 6F is 0. Now 20, if you look at 20, that should be a space. So if we have a look at that, so 20 in the hex chart, you can see there is actually a space. So it's a computer, it's a number for space in the computer. So when we get to say this, the end of hello world, we then have OD and OA. Now, OD and OA, and obviously it says SAF, so safe for work, not safe for work fish, that should be the other fish, but no matter. But when you get to these two dots, now these two dots, now they aren't in this text file. The text file has a new line in there. So if we look at 0D and 0A on here, now 0A and 0D just means it's just DNA. So D is carriage return and A is new line. So basically what that's done is put a new line in. So carriage return is for older systems. So if an older system looks at that text file, it used to use something called carriage return, but now we use new line. So it puts both in just to cover both bases. And modern computers know that if it's got both in, it just ignores one of them. So it's actually put that in correctly. So if we go back to the hex editor, you can see that it's put that in the code there. So that and that to make a new line, and then print all this stuff out afterwards. So that's how it works. It literally just puts them as a massive string of numbers. Obviously, this is viewing it in hex. If you were to view it in binary, it'd just be binary numbers that are put together. You can actually see the 8-bit integer here. It actually tells you which each bond are, so 104. It actually tells you, so you can have a look in the ASCII table if you really want to. And it actually shows you the binary down here, so it shows you which ones are on, which is pretty good. So if we were to have a look, say, at E, so that one, you can see that E is 5, because we did that. So E is the 5 there, and the 2 bits on for lowercase. So it actually does work. It shows you the binary for it. So it literally is just one long string of text, that string of numbers that it stores on a computer, and then because it looks at this ASCII table to see what each character is, it can then print out something that it's obviously used to. One thing of note, which I showed a few people before, is that if you hold the left Alt button on your keyboard, and you want to put in, for whatever reason, your keys are not working anymore and your numpad's only working, so you need to have your numlock on your numpad on the right hand side. If you hold left Alt and type in one of them numbers, so let's say we want to put in a hashtag, so the hashtag is here, and that's number 35. So if you hold left Alt and then put 35 in and then let go of Alt, it will put in a hashtag. And believe me, I have actually done that. I have not just pressed the hashtag button. It does actually do this. For example, if you hold hold Alt and type in 0169 and then let go, it actually puts in a copyright symbol. So it does work. It basically, if you hold the left Alt and then use your numpad on the right, it basically looks through the ASCII table and looks at the number you're typing in. So, that's how a computer works. It literally uses ASCII in order to, search for different symbols that it's supposed to output. So, that is how ASCII works in the computer. It literally just has this table in a file somewhere that it'll look at and be like, right, I know what this number is. I'm going to then present it as an actual character or a symbol. Now, there is extended ASCII, so it goes past, on there it only goes to 127. It can go further than that, so there is extended ASCII, which has got the copyright symbols in and stuff, so you can have a look at that as well if you want to. It's literally just the same thing, it just has more symbols in there other than just letters and numbers and things we normally use. But there is one other thing that you'll need to have a quick look at, which we'll talk about in more detail at another time. But Unicode is a similar thing that's used instead of ASCII. ASCII, for those who don't know, is the most up to date version that's used. So ASCII was used after Unicode. So Unicode was brought out in the 1960s. It was used basically the same way as this is, but it had extra characters in there. Now, ASCII removed some of these because it thought that, you don't really need it, and it's just wasting space, which obviously in the 60s was a big thing. But Unicode's still used. It's used in a lot of modern systems, and Unicode's usually used for storing emojis and stuff like that now, instead of some other things that we don't really need anymore. So you can have a look at that. But it works the exact same way as ASCII does. It's literally just a different set of numbers with a different set of values in there, and that's it. So yeah, that's how ASCII works and how basically Unicode works in a computer. How it looks it up, how it calculates how to swap between them, and obviously how it stores it and then brings it back. So yeah, um, something to have a think about. As I say, have a mess around with the ASCII buttons as well. See what symbols you can get out of it, because there are a lot. There are a lot of numbers in there you can have a look at. Obviously, with extended ASCII, a lot of modern systems have it. So have a look at extended ASCII if you want any fancy symbols that you want. But yeah, that's ASCII. And there'll be some more videos on vectors and bitmaps.